Okay, this is your bell assignment for today. Please get working on that. And whenever you're finished, you may go to the board and put up your answer for your answers to be gone over. You'll have to pause the video so that it doesn't move to the next slide. What we're talking about today is Lesson 59, Experimental Probability. When discussing probability, we distinguish between the theoretical probability, which is found by analyzing a situation, and the experimental probability, which is determined statistically. Experimental probability is the ratio of the number of times an event occurs to the number of trials. So, the experimental probability is equal to the number of times an event occurs divided by the number of trials. For example, if we were flipping a coin here, and I flipped a coin 10 times, let's say, and in those 10 times I got heads 3 times. Well, heads is the event that's occurring, so it happened 3 times. So I would put 3 with my number of times the event occurred over the number of trials. I flipped the coin 10 times, so I would have 3 out of 10, 30%, 3/10, however you want to say it, and that would be my experimental probability. If we want to experimentally determine the probability that a flip coin will land heads up, we will flip the coin a number of times, counting the number of trials and the number of heads. Okay, so across the top here, this whole top is the trial. How many times you have actually flipped the coin. Okay? The next line is the outcome. H and T represent heads or tails, whatever it happens to fall on. Okay? And the bottom is the probability. This is if they plug it in to that equation. The number of outcomes over trials, the total number of trials. Okay, so that's where they're getting each one of these. So, for example, this first one, I have one head out of one try, so that gets me 100%. However, if I get over here to my sixth trial, I know that I've tried 6 times, so that's going to be my denominator, and I have 1, 2, 3, 4 heads. So 4 out of 6 reduces to 2/3, which as a decimal would be that 0.67. So that's where they get each of those from. As the number of trials grows, the experimental probability tends to approach the theoretical probability of an experiment. Therefore, we want a large number of trials when conducting probability experiments. Now, if I were in the room today and we had time, we would do an actual experimental probability experiment. And I would give everyone in here a penny, and I would tell each of you to flip that penny 10 times and record how many times you get heads out of 10. So you'd tally up your answers, and then we'd write everyone's name on the board, and we make one big chart. And I would say that whoever gets 3 out of 10 heads, somebody else gets 6 out of 10, somebody else gets 5 out of 10, so on and so forth. It's not everyone will always end up with this perfect 5 out of 10 times. Okay, so when we do that, if there are only 10 of you in here, or say there are 20 of you in here, if there are 10 of you in here, instead of getting 10 flips, I get 10 flips times each of you. So 10 times 20, that gives me 200 flips. That's a lot better trial number than if we just use one of your results, because one of you may end up only getting 2 out of 10. That happens. It's whenever we take that overall experimental probability average that it ends up coming back to this 50%. Experimental probability is used widely in sports. If the basketball player makes 80 free throws in 100 attempts, then the probability of the player making a free throw is 80 out of 100 or 4 out of 5. The player might be described as an 80% free throw shooter, which is true unless you are on the Milan Middle School basketball team, and then I guarantee you that you're not an 80% free throw shooter. I watched your ball games. Okay? In baseball and softball, a player's batting average is the probability expressed as a decimal of the player getting a hit. So if anybody in here watches MLB, you're a Cardinals fan, hopefully not a Royals fan, and whenever a batter comes up, they'll give that batter's probability, that batter's batting average in many ways. They may say that the batter has a batting average of 333 for the season, but has an average of 475 against this team, or 475 against this team, but 500 against this pitcher. I mean, they have so many different batting averages under so many different circumstances. So they give you all those numbers every time they're up to bat. For example, a softball player has 21 hits in 60 at-bats. Express the probability the player will get a hit in her next at-bat as a decimal number with 3 decimal places. And generally, it's a rule of thumb that 3 decimal places is how they tell batting average. Okay, they run it out to the thousandths place. So we know that our formula for this is the number of outcomes over the number of trials. Okay, the outcome that we're wanting is for that batter to get a hit. So she got 21 hits. And then, oh, hold on just a second. Okay, I apologize for that. So she had 21 hits out of 60 at-bats. Whoops. 60 at-bats. And when we punch this into our calculator, we should punch in 21 divided by 60. Now when we do that, we're going to get 0.35. But they tell us as a decimal number with 3 decimal places. So a way for me to get that third decimal place, we know that behind this 5 is an understood 0, 0, 0, 0, however many zeros you want to show. 350 thousandths is the same as 35 hundredths, so it doesn't change the value there, and we would say that that batter has a 350 batting average. Whoops, too far. A salesperson distributed free samples at the mall. 50 shoppers accepted the samples and 30 did not. What was the probability that a shopper at the mall will accept the salesperson's samples? So you see these people whenever you walk through Walmart, they're giving you little food samples because they want you to buy their product. Okay, so the same thing happens at the mall. And they're wanting to know the probability of a person stopping and accepting the sample. So that is our number of outcomes. The people who stop and get that sample. And the number of trials then is going to be the number of customers that walk by. So it says that 50 shoppers accepted the samples and 30 did not. Well, we want to know how many accepted, so we say 50 shoppers accepted over the total number of shoppers that walked by. 50 accepted, 30 did not, so we had a total of 80 shoppers. So I can cancel that 0 out, and then I punch into my calculator 5 divided by 8, because we know that that fraction bar literally means to divide. And whenever I do that, I get 0.625. To change this decimal into a percent, remember we can take that decimal place and we can move it 2 times to the right, which gets me 62.5%. So 62.5% of the time, the customer will stop and pick up a sample. The commuter plane arrives on schedule 2/3 of the time on any given weekday. Heather wonders what the probability is that it will arrive on schedule on a Tuesday, Wednesday, and Thursday in the same week. How could the experimental probability be found? Why is it impractical? Well, for it to be experimental probability, you actually have to do the experiment. So, for her to check the probability of it arriving Tuesday, Wednesday, and Thursday in the same week, she'd have to go Tuesday, Wednesday, and Thursday in the same week to check and see what number of the flights arrived on time on all those days in 1 week. Okay? Now, whenever some of you may or may not have flown before, okay, but sometimes whenever we are going to fly, there are other factors that change things. For instance, the weather. So, if you are going to the airport and it's, say, the middle of July when it's nice and warm outside, not a whole lot of bad weather going on, and you check this for a week, you may have better numbers. More of the flights may be coming in on time in July than, say, December, when maybe we're in the middle of a blizzard or there's ice or whatever the heck's going on that planes can't fly through. So that's why it's impractical, because it would take you too long to get enough data to be um, true. And then it says, how could the spinner at the right be used to simulate the experiment? Well, instead of going for 52 weeks out of the year and checking Tuesday, Wednesday, and Thursday, she could just chart it and say, okay, on Tuesday there are going to be 20 flights. Let's see how many of them arrive 2/3 of the time. And Wednesday, same thing. Thursday, same thing. And she could just do that for however many times she wants to, instead of going and sitting at the airport all day by herself. Homework is going to be from Lesson 57, A through E, 1 through 15 odd, and 16 through 30 even. This is going to be due tomorrow whenever you walk into the classroom. You need to be working, not talking. Please make sure that the assignment gets written on the assignment board. And be good. Have a good day.